Bismillahirrahmanirrahim. Our today's lecture is on flexure analysis and design of beam. Again, we will see in this lecture some basic concept regarding the flexure analysis and design of beam using ASD method. First of all, we will discuss various types of cracks. Actually, we have three various types of cracks that were developed in the beam. First type of crack we called as pure flexure crack. Pure flexure crack are normally appeared at a point where we have maximum bending moment. So where we have maximum deflection, we can also say that. So these vertical cracks are actually initiated from the tension phase and moves towards the neutral axis. So you can see that if this is the compression phase, this is the tension phase, these cracks are propagated from the tension phase and move vertically towards the neutral axis. Second type of crack we called as pure shear or web shear crack. Actually, these cracks are appeared at the neutral axis and propagate in both directions. So this is the neutral axis and it initiate from the neutral axis and propagate actually in both the direction. The angle between that crack, as that crack is inclined, that is 45 degree. The reason being is that if we draw a Mohr circle, we know that the angle between maximum principal stress and shear stress, that is 90. And we know that if 90 is the angle in Mohr circle, then on actual element it will be half. So half of 90 is 45. So these inclined cracks needs to be at 45. And this we called as pure shear or web shear crack. This is the example of pure shear crack. You can see that these cracks are roughly at around 45 degree. These inclined cracks. These are the pure example of physically field example of shear crack. Now next type of crack we call as flexural shear crack. As the name indicate, this crack has the shear crack as well as the fracture crack. In the region of high shear due to diagonal tension, the inclined crack developed as an extension of flexural crack and termed as flexural shear crack. This is the schematic diagram of flexural shear crack. Now, tensile strength of concrete. Actually, there are considerable experimental difficulties in determining the true tensile strength of concrete. So, in direct tension test, actually we have the following difficulties. First of all, when concrete is gripped by the machine, it may be crushed due to large stress concentration at the grip. Secondly, concrete sample of different size and different diameter may show large variation in the tensile strength. Again, in third point, if there are some void in the sample, the test may show very small strength. If there is some initial misalignment in fixing the sample, results may not be accurate. So, just we perform like a tension test on the steel rebar, we cannot perform the same test on the concrete specimen. So there are some indirect method by which we can determine the tensile strength of the concrete. First method we called as split slender test. So we will place the slender like that in the machine. We will apply the load and note the reading until it split apart. So this test is performed by loading a standard 150 mm diameter and 300 mm long slender by a line perpendicular load to its longitudinal axis, with slender placed on the testing machine platen. The tensile strength can be defined as Ft is basically denoting the tensile strength equals to 2P divided by pi dl. P is the total value of line load noted by the machine. D is diameter of the concrete cylinder and L is the cylinder height or length. Next, indirect method of measuring tensile strength of concrete is actually double punch test. In this test, cylinder is placed vertically between the loading platen of the machine and is compressed by two steel punches placed at the top and bottom end surfaces. The sample will split across many vertical diametrical planes radiating from the central axis. So tensile strength can be determined. Ft is Q over pi into 1.2 BH minus A square. Q is the crushing load, H is the height of the cylinder, and 2 is basically the diameter of the steel punch. Other test we call as modulus of rupture test. For many years, tensile strength has been measured in terms of modulus of rupture. Modulus of rupture is denoted by Fr, the computed flexural tensile stress at which test beam of plane beam fails. Because this nominal stress is computed on the assumption that concrete is an elastic material, and because this bending stress is localized at the outermost surface, it is larger than the strength of concrete in uniform axial tension. It is again an indirect method of determining the tensile strength, but it is not identical with real axial tensile strength. So what we will do, actually, we will cast a beam and we will apply actually 4-point loading. So this is 1 point, 2nd point, 3rd point, and that support is also acting as a 4th point. Sometimes we also called as 2-point loading if we are just considering this point and this point. We will apply the load and note down the load at which the crack initiates. Now some relationship between modulus of rupture and compressive strength of concrete. Fr, modulus of rupture, is equals to 0.69 lambda under root Fc dash. Fc dash is basically compressive strength. Lambda is modification factor for lightweight concrete, and it is considered as 1 for normal weight concrete. ACI code has also given a formula which says Fr is equals to 0.5 times lambda under root Fc dash. Lambda is again 1 for normal weight concrete. For deflection control criteria, modulus of rupture is 0.625 under root Fc dash. Now few empirical formulas which relate the tensile strength of concrete and compressive strength of concrete. So Ft is 5 by 12 under root Fc dash. Again, Ft is 1 by 4 of under root Fc dash. These are some relations which relate tensile strength and compressive strength. Normally we can say that tensile strength of concrete is 8 to 15% of the compressive strength. Normally we consider 10% of compressive strength may be considered as the tensile strength of concrete. Now transform section. Beam is a combination of concrete and steel material. Therefore, we can say that it is not a homogeneous material. In transform section, actually the steel area is replaced with the equivalent concrete area in order to calculate these section properties. So if these steel rebars replaced with equivalent concrete area, that particular type of section we call as transform section. This width of extended area is same as the diameter of the steel rebar is, and its distance from compression phase remains the same. Actually, we do not have physically that extended portion. We will just consider the same equivalent area as the steel has in order to replace with the equivalent concrete area. Now modular ratio. Modular ratio is a ratio of modulus of elasticity of steel to the modulus of elasticity of concrete. Normally its value is 8 to 10. It is a unitless quantity. Uncracked transform section. When both steel and concrete are in elastic range and tensile stress at the tension phase of the concrete is less than tensile strength of concrete, this section is called as uncracked section. Within elastic range, actually perfect bond exists between steel and concrete, which means that strain in steel is equals to strain in concrete. So epsilon S is equals to Fs divided by Es equals to Fc divided by Ec. So if we do some rearrangement, Fs will become equals to Es divided by Ec into Fc, or we can say that Fs stress in steel equals to modular ratio times stress in concrete. So using this relationship, stress in steel can be calculated if we know the stress in concrete and modular ratio. Now uncracked transform section. Consider a beam having steel area equals to AS. In order to obtain a transformed section, the area of steel is replaced by an equivalent area of concrete so that same forces is developed in both. So force in steel PS is equals to force in concrete. P is equals to stress time area, so Fs into As equals to Fc into AC equivalent. This AC equivalent is equivalent area of concrete. We know that Fs is equals to N times Fc, As equals to Fc, AC equivalent. So we can say that this Fc will be cancelled out with this Fc. Now area of concrete equivalent is equals to N times AS. So in case of transformed section, so instead of that steel reinforcement, we will produce actually an equivalent transformed section which consider the equivalent area of concrete. So half of N times AS divided by 2, half of area on one side and half of area on the other side we will provide it. Again remember, we will not show that physically, you cannot see any beam physically extended outside. This is just for the analysis purpose, just to show that half of equivalent area of concrete is provided on this side and half will be provided on that side in order to consider a transformed section. Now the equivalent area NAS by 2 is shown on either side, but steel inside the beam is removed, which creates a space that is filled by area of concrete. Thus the equivalent area on each side becomes NAS by 2 minus AS by 2. So N minus 1 times AS by 2, that area needs to be provided on both sides in order to get a transformed section. Once the transformed section has been formed, the sectional properties are calculated in a usual manner. So total area of transformed section is B times H plus N minus 1 into AS, or we can say that gross AG plus N minus 1 into AS. So this is basically the transformed, uncracked transformed section. In this particular lecture, we have studied some basic concept regarding flexure analysis and design of beam using ASD method. I would highly recommend to read chapter number 2 from Zaid Ahmed Siddiqui book. Thanks.